Now, let's have an example of finding the inverse of a matrix if it exists. So we're given here with a matrix, and we want to know how can we find the inverse of this matrix if that matrix exists. So first, we shall check. The size of the matrix is 2 by 2. So that would mean that it's a square matrix, and therefore it is possible that it has an inverse. So how do we find the inverse of this matrix? The key is we're going to perform Gauss-Jordan elimination. Gauss-Jordan elimination. So this process or this algorithm will require the use of Gauss-Jordan elimination. And how do we do it? First, we write our given matrix, and then we adjoin it or we connect it to the identity matrix of its size. So this is I sub 2. So I'm going to have 1, 0, 0, 1 here. Now this matrix that we have here, this is where, or this is the matrix that we're going to perform our Gauss-Jordan elimination, in such that we are, so to speak, transferring this identity matrix here to the other side. And the resulting matrix here will become the inverse of the given matrix. So let's try it out. This is our given matrix that has been adjoined, and I want to make it an identity matrix. So first, what I'm going to do is add row 1 and row 2 to get a new row 2. So that's row 1 plus row 2. So I'm going to have, first I'll copy row 1. So there you go. 1 plus negative 1 is 0. 4 plus negative 3 is 1. Then I'm going to have 1 plus 0 is 1. 0 plus 1 is 1. So there. Next, I have to turn this to 0. So therefore, I'm going to have row 1 would be negative 4 times row 2 plus row 1. And that would give me, well, this is 0. So 0 times negative 4 is 0 plus 1 is 1. Negative 4 times 1 is negative 4 plus 4 is 0. Negative 4 times 1 is negative 4 plus 1 is negative 3. Negative 4 times 1 is negative 4 plus 0 is negative 4. Then we keep the second row. Now, as you can see here, let's write it here instead. We have 1, 0, 0, 1, then negative 3, negative 4, 1, 1. So as we can see here, this has already been our identity matrix, while the matrix formed here has become our inverse. So therefore, we can say that the inverse of this matrix A is the matrix with the elements negative 3, negative 4, 1, 1. If you would like to check if that is correct, you multiply this matrix to this matrix, and you're going to get I sub 2. This time, it's your turn. Here we have a given matrix A. Pause the video and try to solve for the inverse of this matrix. Alright, so like what we mentioned, the first thing to do is to write this matrix. Before that rather, we identify this is a 3 by 3 matrix. So that means we can get its inverse, and we're going to relate it to I sub 3. So therefore, we'll have 1, negative 1, 0, 1, 0, negative 1, negative 6, 2, 3. Oops, sorry. We should not end it there. Instead, we shall connect I sub 3. 1, 0, 0, 1, 0, 1, 0, 0, 1. So there. So we perform Gauss-Jordan elimination on this matrix. So leaving the Gauss-Jordan to our viewers, we're going to get the resulting matrix here as, we're going to have, of course, that's 1, 0, 0, then negative 2, negative 3, negative 1, 0, 1, 0, negative 3, negative 3, negative 1. Then here, 0, 0, 1, we're going to have negative 2, negative 4, negative 1. So we were able to find an inverse. So this would mean that the inverse of A is the matrix whose elements are -2, -3, -1, -3, -3, -1, -2, -4, -1. Again, the process of the Gauss-Jordan elimination is left to the viewers. Now, this time, we are asked to show that this matrix has no inverse. We know that this is a 3 by 3 matrix, and hence we can relate it to I sub 3. But, like what we mentioned, not all square matrices would have an inverse. So let's check. So, let's write our given matrix alongside our I sub 3. There you go. Oops, I wrote it a bit small. So there. So let's now perform our Gauss-Jordan elimination because that's the only way to know if the matrix has an inverse or not. So I want to make these 0. So that would mean that I'm going to change my row 2 to having -3 times, oops, written too far. -3 times row 1 plus row 2, and I'm going to change my row 3 to multiplying to 2 times row 1 plus row 3. So, my row 1 does not change. Oops, that's a bit far. My row 1 does not change, but my row 2 will become 0, -7, 2, -3, 1, 0. My row 3 will become 0, 7, -2, 2, 0, 1. So there we go. Now, since we're making this Gauss-Jordan, I should make this -7 as 1. So therefore, my row 2 should be changing to, I should multiply to -1, 7, row 2. So I'm going to have still the first row as is. My second row becomes 0, 1, -2 sevenths, 3 sevenths, 1 seventh, 0. Well, this one here is 0, 7, -2, 2, 0, 1. There you go. Now, since this is 1, I would have to change now my R1 and R3. So, oops, let's write it here at this side. Let's hope it fits. For row 1, I would have to change it to -2 times row 2 plus row 1. While for row 3, I'm going to have -7 times row 2 plus row 3. So there you go. My row 2 will not change, so I'll just copy it. -2 sevenths here. Oops, sorry about that line. Then this is 3 sevenths, 1 seventh, and 0. So for the first row, I'm going to have 1, 0, 4 sevenths here, 1 seventh, -2 sevenths, 0. For row 3, I'm going to actually have 0, 0, 0. And I'm stopping here. As you can see, we have zeros here. This would mean that this cannot be turned into I sub 3 because this should be 1. But since we already had zeros here, it would be quite difficult for us to get a 1, which would mean that this side, the left side, cannot be I sub 3. And because of this, we can only conclude that our given matrix A has no inverse. So, when we're performing our Gauss-Jordan elimination, once we see that one of the rows has become all 0, it cannot be turned, the left side rather, cannot be turned into an identity matrix. Hence, the given matrix has no inverse.